This is a presentation of the 19th Annual Colorado Snow and Avalanche Workshop, a program of the Colorado Avalanche Information Center, Friends of CAIC, and the National Avalanche Center, presented by Dinafit and Pomoka.
Hi, and welcome to my talk about how we retrieve avalanche-relevant information from space data. My name is Regula Frauenfelder, and I'm a principal engineer and senior researcher at the Norwegian Geotechnical Institute in Oslo, Norway. The motivation for our work is that we want to be able to identify, map, and use information which is relevant to avalanche warning and in avalanche modeling. We would like to do that before avalanche releases and after avalanches have released. You see here a black and white satellite imagery taken from 500 kilometers above ground. If you zoom in, you can see an incredible amount of detail. You see the avalanche deposits, you see the bare rock in the slopes where the snow has released, and you see also where the snowpack is not impacted by the avalanches. This type of data is the data we want to exploit in our work. The beauty of remote sensing is that you can cover large areas. It allows safe access to otherwise dangerous terrain, so it does not jeopardize staff safety. It also allows to acquisite a lot of data that can be processed fast. And some of the sensors are even independent of weather and illumination, so you can use them both during daytime and at night, and during the polar night in Arctic areas. However, as every method, also remote sensing comes with some drawbacks. One of it is that the freely available data has mediocre resolution. It's often around 10 by 10 meters or coarser. There exists much higher resolution data down to half a meter, but this data comes at a considerably high cost. In addition, in high mountain terrain, actually there where we have to count on avalanches, relevant areas can be hidden. This can be due to shadow areas in optical imagery or to what we call distortions and layovers in radar imagery, which is caused by the fact that the radar is looking from the side onto the steep topography. I will now first talk a little bit how such type of data could be used before avalanches have released, before the onset of big avalanche cycles. Here we are mostly interested in the precursors. We want to identify and map relevant parameters such as the initial status of an avalanche cycle, the status of indicator avalanches, surface hoar, or wet snow. You see here a map of the southern part of Norway with different type of wetnesses of the snow. The light blue color indicates dry snow, purple is moist, and yellow is wet. Green is bare ground. So the vision is that in addition to be able to flag such areas, at some time we will also be able to flag critical areas, for example, where we have surface hoar, which then could be snowed in and generate a weak layer, like you see in the nice image by Bruce Jamieson in the lower image. And we want to be able to flag such critical areas in due time to be considered in the preparation of avalanche danger warnings. It's quite a difficult task, and different types of groups are working on these topics. So we actually have come farther when it comes to how we can exploit this type of data after avalanches have released. And that will be the main part of my talk. Here we are interested to identify and map avalanches and mainly avalanche deposits and run outs on the paths. Why would we want to do that? In a non-real-time context, we want to do it to evaluate or validate issued warnings by hindcasting with a statistically sound data set, because we believe that this will lead to improved warnings. The vision here is also that it can be used in a much more near real-time or real-time sense, to be captured during big avalanche cycles and can be directly made available to the avalanche forecasters. I will show you some examples now how we do this with optical satellite imagery. Here you see again a world view 1 image from an area in the Czech Republic, from the Tatra Mountains. Again, as a human observer, you will be very easily able to identify the avalanche deposits from the bare snow, from the glare, and from the rock slopes. Now the challenge is how we can train and develop an algorithm that is able to do the same, and maybe even can look better into shadowy areas than we can as a human observer. We have used quite some time and put some considerable work into developing such algorithms, and this is the first example where you see how the algorithm works. In green, it was able to detect the avalanche snow, and it was also able to differ the rock outcrops and the areas with glare and the undisturbed snow surfaces. You will also see, if I go back, that there are certain differences in the run-out lengths of the avalanches. So in certain type of snow, the algorithm struggles to delineate exactly between the avalanches and the non-impacted snow. However, overall, the results are quite satisfying. Here you see a larger portion of that image, and these are the outlines that were delineated, digitized by a human expert at NGI, an avalanche forecaster. And her task was to digitize all the observable avalanches. On the next image, you see the same result done by the algorithm. And the third image shows you the comparison between the algorithm and the delineation by the avalanche experts. The blue area shows areas where the human expert and the algorithm agree with each other. The yellow areas show where the algorithm was able to detect the avalanches, whereas the human observer was not able to do it, or maybe she just thought it was too cumbersome, because you see it's mostly the areas up high in the rock outcrops. And then you also have the pink areas where actually the algorithm was not able to capture the avalanche deposits, whereas the human expert was able to do so. Still, despite these deviations between the human observer and the algorithm result, we think that the overall result is quite satisfying. Therefore, we have used this algorithm to delineate the entire Czechian, Slovakian Tatra Mountains after a very big avalanche cycle in 2009. We were able to depict several hundred avalanches and deliver them right into the database of the Slovakian Avalanche Prevention Center. This would not have been possible for them by just in situ observations or field observations, so it was absolutely crucial for them to have such type of satellite data at hand. One of the drawbacks of optical imagery is, of course, that it cannot penetrate clouds. And we all know that avalanches always come together with bad weather. So one solution to circumvent this problem is to use radar satellite data, because a radar satellite is able to penetrate clouds and is also independent of illumination conditions. What you see here and what looks like a normal hillshade of an area in northern Norway, it's actually a so-called backscatter image. A backscatter image is what you get when you send a radar signal to the Earth and measure what's reflected back from the Earth's surface. Depending on the surface characteristics, like the roughness or other type of characteristics, the signal will be bounced back directly and smoothly or indirectly. And this will give you a difference in what we call the backscatter. Here, the black areas is actually water in the fjords on the sea, and all the grayish and whitish area are then the land surfaces and the terrain. I would now ask you to concentrate into the middle of the picture, because I will now go to the next picture. The first one here was taken in the middle of December in 2014. the next one is taken on the 6th of January in 2015, so just after New Year. If you see in the middle of the picture, you see these white blobs that have arisen. I go back again. They're not there, except from two small ones. If I go further again, you see quite many of these white blobs in the image center and also a little bit up to the right corner. If we now differentiate these two pictures by subtracting one from the other, that's the next image, you see them as green highlighted blobs or cluster of cells. And these are actually the avalanches we are interested in. So the white areas, that's where we have no data due to this radar distortion that I shortly mentioned initially. The gray areas, that's where we have no change between the December image and the January image. The purple areas is where we have wet snow. So the snow got wetter between the December image and the January image. And finally, the green area, as I said, that's what we are interested in. That's the avalanche deposits. It's quite easy to extract these green areas also with an algorithm that does this automatically. And then on the next picture, you see we end up with just the red avalanche deposits here highlighted on a standard hillshade of the terrain model. And these avalanche outliers you can then again use into your database, either to calibrate your models or if you get them real time to judge the onset of your avalanche cycle. The beauty of radar data, of these radar satellites, is that the higher north you come, the more often you will get an image. So actually in the high Arctic, you can get an image as often as maybe every second day. And even at mid-latitudes, around 40 to 50 degree north, you can have an image several times a week. And this, of course, makes it very interesting to use this data repeatedly. And that's actually, and yeah, sorry, here you see the avalanche deposits again. And that's actually what the Norwegian Water and Energy Resources Directorate is doing right now. They're now operationalizing this service for entire Norway. Here you see an area in northern Norway where they made a test in the winters 2016 to 2018, where they were able to detect approximately 5,000 avalanches per winter by using this type of radar data, versus generally about 100 avalanches per winter that were reported manually. So you see, the potential is huge to really be able to map many, many more of the avalanches that actually have released than you would if you would not be able to use this data. So we're looking forward, at least in Norway, to be able to take this type of data in use from this winter on. You also see here a comparison on how they, when they checked how the algorithm that depicts the avalanches automatically, how this looks like in comparison to GPS tracks or to a manual delineation by a human observer. And as for the optical example that I showed you, I think the result is quite satisfying. At some point, it's also nice if you can exploit both types of data in combination, because also these optical satellites actually have quite a tight revisit time, meaning also they come by the same area quite often. And here we did a test for the Alaskan highway between Anchorage and Seward a couple of years ago, together with the Alaskan Department of Transportation. You see in yellow, you see the highway, and in these yellow blobs delineate their avalanche passes that can reach the road. They have quite a pronounced glide snow avalanche problem, especially in springtime. And so they were interested to know how they can use this type of data in their in capturing the avalanche cycles along this highway. Here you see the first change detection with radar imagery between January and February in 2016. And you see in yellow the notorious avalanche paths that they are interested in, the avalanche paths that potentially can reach the road. You see that it's calm in there, nothing has happened yet by early February, but you see that a bit further down to the left of the image, some of the avalanches have released. again, you see that as these green blotches. By March 6th in the same year, this is an optical image now. You see that still this path that they are interested in, nothing has happened there. The situation is still calm. Whereas in the next one, we are now in the middle of April, you see that to the west of these paths, a lot of avalanches have started to release. And also in the middle, in the biggest pass, some of the snow has started to release. The SAR image is then the change between March and April, so slightly after the last optical image that we just showed, and you can see the same avalanches that have released to the west of the main pass, but you also see that in the main pass there has released a new small avalanche to the right of the path. Then here in a new optical image, and as I said, they have problems to penetrate clouds, and that's obvious here. Still, it's possible to see that the snow starts to deplete in lower areas. And then by mid or end of May, you can actually see that the entire area is mostly depleted of snow and the situation has calmed down. So this is just an example to show how you can use this type of data in combination, the optical data and the radar data. With this, I would like to sum up, and I hope I could show you that satellite imagery has a large potential for applications within avalanche monitoring and avalanche forecasting. I also have to say that it's most suited for bigger institutions, such as regional or national avalanche forecasting services or authorities, because you need quite some resources to be able to make an operational use of this type of data. I showed you that very high resolution optical imagery is most applicable to update avalanche databases after large avalanche cycles. So once the good weather has set on again and you're able to actually capture good optical imagery. Whereas the radar data is most feasible in near real-time or real-time oriented applications because it's independent of clear sky and illumination conditions. And therefore you can use it very close up to avalanche cycles and almost continuously within your avalanche forecasting framework. Here I also show you some references for those that are especially interested. With this, I would like to thank you for your attention and conclude my talk. If you have more questions, just send me an email to rf@ngo.no. Thank you.